Morning. Morning, good morning. How are we this bright and early morning? It is too bright and early. Can we hear me? All okay? Howdy, howdy, howdy. Howdy, howdy, ho. This is a little cup. This is one of my little cups. You should see my big cups. The little cup. I know, it was getting close to 9:30. I didn't do a good job about starting early enough this morning, getting it set up. I got it all set up, but I didn't start the computer part of it. So I have to start on the computer, getting it all connected bright early so that it'll talk to one another. How are y'all? Ready to go? So I early bird this morning. See if you can do this. See if you can at least get it started from what we did last week. Our early bird this morning is to create a probability distribution for the number of heads when flipping 3 coins. Remember, you created probability distributions last week and the week before that in your tasks. You had to create those probability distributions. So see if you can do that here. Create a probability distribution for the number of heads when flipping 3 coins. So if I flip 3 coins, how many heads could I get? And what's the probability of each of those? Morning, Jasmine. Morning, Kelsey. Hey, Bo. Hey, Kara, Adam. Priscilla, did I miss anybody? I wonder if Mr. Simpson's on yet this morning. So today we're going to do expected value. Hopefully last night's homework wasn't too bad. Morning, Mr. Simpson. There he is. Some of y'all did great yesterday. You got that homework done and then you got it turned in. Yay! And I was able to grade a bunch of it and get it back to you. So if anybody made an error, if you've gotten feedback from me, you already know, oh, I need to redo it, or I need to fix this, or you know, yay, I did it all perfect. I can cross that one off my list and not worry about it. So you did great on getting that done yesterday. And hopefully today's will go just as quickly. And you can get it done, get it turned in, and do the same thing with it. All right, let's go ahead and get started on this expected value. So for the expected, hey, Eve, good morning. For this expected value, what we're going to do, the first thing you're going to need to do each time is to create a probability distribution. So in the last 2 tasks, you've done that. You've gotten to practice making a probability distribution. And so hopefully that'll help as we move into this lecture, into finding the expected value, because that's going to be our first task, is to find out, to make a probability distribution. So, how many heads could I get? What are the different, my random variable here is the number of heads. So how many heads could I get? How many heads could I get? What are the potentials? What are the possible outcomes? Let me grab a black here. I could get 3. Good. I could get 0 to 3. Yeah. So I wouldn't have to get any heads. I could flip that coin over and over again and not get any. Good, guys. There you go. And carrot. Good, Jasmine. 1, 2, or 3 heads. Those are the potential number of heads that I could get. I can't get more than 3 because I'm only flipping it 3 times. And I can't get less than 0 because, you know, none is the smallest I can get. Perfect, guys. Now I want to know what's the probability of each of those. So how would I go about finding the probability of each of those? How could I find out the probability that I get 0 heads? How could I find out the probability I get 1 head? How could I find out the probability I get 2 heads? So we've done this in the past on those last 2 tasks, maybe not with flipping heads and tails, but we've done it. How can I find out the theoretical, not the, if I wanted to find out the empirical, I would flip the coin. But what about for the, to find out the theoretical one? Yeah, if I wanted to find out that empirical, I would definitely flip the coin and find out the probability. But in theory, how would I do it? So Bo says, look, there are 2 outcomes, heads and tails. There are 3 flips. I'm going to do it, or at least I'm going to, flip 3 coins. So, you know, I've got a fixed number of times there I'm doing it. So now, what is that? What does that make you think of? Does the probability stay the same or not? Oh, another way to do it would just be to do it with brute force. To say, oh look, I could do a head, or I could do a head, a tail. You know, we could make that whole tree. We could make the tree to find out the brute force. I could say, well, the first flip, I could get a head or a tail. You remember doing that, making the symmetric sample space? We could do it this way. Second flip, we could do a head or a tail. So we could do it through brute force, or Bo and Adam say, look, this is just binomial. Why not just use the binomial distribution? Whichever way you like best. The reason we learned this symmetric sample space is sometimes maybe it's easier just to make the symmetric sample space of all the outcomes. So, you know, we could do it like we did with the head and head, or head and tail, or head and tail and head, or we could just use the binomial. Either way, we're going to end up with, here's 3 heads. This is 2 heads and 1 tail, 2 heads and 1 tail, 1 head and 2 tails, 2 heads and 1 tail, 2 tails and 1 head. It would have been easier just to do the heads. 1 head and 2 tails, or 3 tails. So just looking at the heads, that's all we care about are the heads. So we've got 1, 2, 3, 8, 3 out of 8 potential things. This is 0 heads. 3 out of 8 gives me 2 heads. 3 heads just shows up 1 out of 8. 3 out of 8 is 1 head, or 1 out of 8 is 0 heads. Or maybe use binomial. I like the binomial idea. If I'm doing binomial, the probability I get 0 heads, well, I do 3 choose 0 times the probability I get a head is 1/2 to the 0 power times the probability I get a failure, a tail, is 1/2 to the 3rd power. Well, hopefully by now you're getting really good at this combination thing. So anytime you've got to choose 0, it's just equal to 1. Raised to the 0 power is 1. And then I've just got 1/2 times 1/2 times 1/2, which sure enough equals 1/8. So you can see it on the tree. You know, if we just brute forced, went through it, or you could use binomial. So the probabilities of each, use binomial or use your tree, either one, and find out that these are your probabilities of each of those. Hey Zoe. So to be able to do to be able to find the probability distribution is going to be step one. So all that we've done with finding probabilities in the past, you're going to need in order to make your probability distribution for today's lecture. In order to find the expected value, the first thing you're going to have to do is find this probability distribution. So you can see that using those probabilities, maybe doing binomial, maybe doing a tree, maybe just brute forcing it, you know, like we did with the classical, writing down the words, or just thinking about those different probability rules. All of those are going to come in handy today. Okay, once we've done our probability distribution, then all the expected value is a weighted mean. That's all it is. So, now I want to know, I'm now going to find the expected number of heads. Okay, so, you know, if I'm just doing this experiment one time, then I could get any of these outcomes. But if I'm having a whole classroom of people, a whole group of people do this experiment where they're flipping 3 coins and they're counting the number of heads that they're doing. And I want to know what, on average, how many heads are people going to get? On average, you know, maybe I'm running a booth at the fair and I want to determine prizes or not prizes. You know, how many prizes, what prizes should I give? And for what number of heads should I give it out? So for whatever reason that I'm trying to find out that average, and I have a bunch of people coming to me to flip 3 coins, then that's what the expected value does, is it says on average, how many flips, how many heads should I expect? Should I expect them to, on average, get 0 heads, 1 head, 2 heads, 3 heads? On average, what's going to happen? And all that average is a weighted mean, because we know that in theory, 1 out of every 8 people should get 0 heads. And in theory, 3 out of every 8 people should get 1 head. In theory, 3 out of 8 people should get 2 heads. And in theory, 1 out of every 8 people should get 3 heads. So think about if it worked out theoretically like it's supposed to. If I had 8 people show up, well then 1 of those 8 would get 0, I think I was saying that wrong. 1 of those 8 should get 0 heads. So let's just picture the 8 people that walk up. And they do exactly what in theory it says it's supposed to do. 1 of them is going to get 0 heads. 3 of them gets 1 head. Get 1 head. 3 of them get 2 heads. And 1 of them get 3 heads. In theory, that's what we said should happen. Is that if I have 8 people, 1 of them should have 0 heads. That tree showed that as well, that this is in theory what should happen. Now if I ask you what's the average number of heads that we got, what you would do is you just add those up and you would divide. So let's do that. Let's just add them up and divide, and then I'll show you the shortcut to it. But this is the idea of exactly what we're doing. So I could just add those up. So 5, 6, 7, 8, 9, 10, 11, 12. And then I'm going to divide that by the number of them there, which makes a total of 8. So I'm going to take that 12 and divide it by 8. So, 12 divided by 8, which gives me, what, 4 goes into both of those, so that's 3 halves, or 1.5. So on average, I should get 1.5. So what Adam said when he's like 1 or 2, well, yeah, it's right in the middle of those. Our average is going to be in the middle of those. Exactly, it's 1.5 is the average number of heads I expect. Now look, nobody can flip 1.5. That's not a number we can actually get, but on average, that's what we expect to happen, is for people to flip 1.5 heads. Now, we did it just by adding it up, looking at it in theory. But just like we did yesterday with the grades, what we can do is multiply the weights times each of the variables. So for instance, here, I'm just going to take the 0 times that 1/8. That's what I did here. It was 1 out of the 8. So I'm going to take that 0 times the 1/8. I'm going to take one of these 3's. One of those 3/8. I'm going to take 2 times this 3/8. It's weighted 3 of those times. I'm going to do 3 times 1/8. I'm going to add those all together. Really, that's what we're doing when we add these up. We're saying we have 1 0, 3 1s, 3 2s, and 1 3. And then we're just dividing early on instead of dividing at the end. That division can be done in either place. So here, I've got 0 plus 3/8 plus 6/8 plus 3/8. Add it together, you got 9s and 11, 12, 8s. I end up with exactly the same thing as I did over there. So all we're doing for expected value is we are finding the weighted mean. It's just the average is what we're looking for. That's what that expected number is if we did this over and over and over again, on average, how many would we get? Kind of makes sense, sort of anyway? All right, let's do some more of this. Let's find some more expected value. So, hey guys, what do you think about my pen? Can you see it? Like my pen? We now have new merchandise. We've got Simpson Math merchandise. We got pens and magnets. So, I know Eve was wanting pens. Look, I got new ones to give out, but y'all aren't in class to give them out. Now you just have to take another class. Now you have to take college algebra or something to earn some pens, or take that route. I know y'all are all wanting to take another math after this. We're all fancy. Simpson Math pens, got magnets, stickers. Mr. Simpson, did you see the pens? Up and coming business we are. Business that makes no money, only spends money. That's what we do. All right. Okay, so here's some other examples of us just finding the expected value. So here we have a board game that uses this spinner to determine the number of moves of a player. I lost my eraser. There it is. Okay, so board game uses the spinner to determine the number of moves of a player. Determine the expected move. So you play those board games with your kids and you're like, is this game ever going to end? How many moves am I going to have to play with my kid in order for, to appease them? So now, after today's lesson, you're going to be able to find out the expected number of moves or the expected number of turns it's going to take in order for you to play a game with your kid. So let's do this one. The first thing we're going to do on all of these, the first thing we have to do is find out that probability. We have to create a distribution. So, I want to know, what are my potential outcomes? If I'm using that spinner to spin, to move on my board game, what are the potential outcomes? What could happen? So that's step one, is to decide what are my variables, or what is my random variable? What are my potential outcomes? Yeah, exactly. Game of life, that shoots and ladders game that we've all played, you know. How long does it take? Advance or retreat? That's right. Which one are we doing? Yeah, we can either advance or go back. You're exactly right. We're either advancing or retreating. And then how much are we advancing and how much are we going back? So you're right, we can either go forward or we can go back, but it's a little more specific than that because we have some options. Good. We could go ahead 4. We could go ahead 6. We could go back 2, or we could go back 8. So I want to know, on average, what's my move going to be. On one move, I'm going to do each of those, but on average, how far am I going to go? So now I want to know the probability of each of those. So what is the probability that each of those occurs? So what is the probability that I go 4? How do I find that out? Oh, good. It's 4 out of the 8. Yeah. And that's because on my spinner there are 4 out of the 8 spots. So it's 4/8 is the probability that I go forward 4. What's the probability that I go forward 6? What, 2 out of 8? So 2/8 is forward 6. What's the probability that I go backwards 2? 1 out of the 8. Oops. Excuse me. I don't know how it does that when it's completely silenced and even got the little car thing on. Oh well. What's the probability that I go backwards 8? 1 out of 8? Okay, so now I want to find that average. Perfect. Good job, guys. Okay, so now I want to find the average. So this is just like before. If I had eight moves, 4 of the times I would expect to get 4. 2 of the times I would expect to get 6. 1 of the times I would expect to go backwards 2, and 1 of those times I would expect to go backwards 1. So I could just add up 4, 4, 4, 4, 6, 6, -2, -8, and then divide those by 8. Or I could multiply by the weight and then add up. I know, in class. Stupid phone. You need to move it into the other room since it's not going to agree with me. Okay, 4 times 4/8. I'm going to do 4 of the times I expect to get a 4, plus 6 times that 2/8. Instead of putting a plus, I'm going to do a minus because this is a negative here. So I'm going to be minusing or subtracting. So minus 2 times 1/8 minus 8 times 1/8. Now I just multiply and add. So really the hardest part of this is figuring out the probabilities of each. So, you know, what is the probability that that occurs? Once I have my outcomes written down and my probabilities written down, then all of a sudden it's just arithmetic. Then I'm just multiplying and adding. By the way, My probabilities should always add up to be what? I could add this up, and what should it add up to be? What should all this add up to be? So that I can kind of check myself each time to see if I've gotten those probabilities. Let's see what this adds up to be. 4, 5, 6, 7, 8 out of 8, or one whole thing. Exactly, good, because that's the whole set. That's exactly right. Perfect. All right, so here I've got, now I'm just doing the arithmetic. So multiply straight across, 16 eighths plus 12 eighths minus 2 eighths minus 8 eighths. You know, I could have probably simplified all those, and it might have made it easier, except these last ones wouldn't have simplified. And then in the end, because I'm adding and subtracting, I would have to go back and find a common denominator. So I didn't simplify here because I knew I was going to be adding and subtracting. Anytime we're adding and subtracting with fractions, we're going to have to find a common denominator. So I just held off on simplifying. So now I'm just adding across here, so that's 28. I'm going to go ahead and add my negatives. So negative backwards 2 and backwards 8 is backwards 10. So 28 minus 10 makes 18. Well, that's what, 9. Divide that by 2, divide that by 2, and I got 9/4, or 2 1/4. Write that as a decimal just for funsies, because sometimes I ask you to write it as a decimal. Sometimes I ask you to leave it as an improper fraction. Improper fraction, or just another way to say that is just a simplified fraction. That's a simplified fraction. This one is a mixed number. So in my instructions, I may tell you to leave it as a simplified fraction. I just mean reduce it down as far as you can go. If I ask you to leave it as a mixed number, well then we're going to divide that out. 4 goes in there 2 times with 1 left over. So that's where the 1/4 comes in. It's 2 1/4. Or I can make it a decimal, and you guys know at this point, y'all have gotten so good that you know that 1/4 as a decimal is just 0.25. So there it is as a decimal. So on average, I expect to move 2 and a little bit, 2 1/4 moves. 2 1/4 moves. Yeah, so what was his, how long do we expect to take to finish the game? But we need to know how many spaces are on that board. So let's say that there are 100 spaces on the board. So I know that there's 225. Let me ask it this way first. I'm going to get to Mr. Simpson's question here in a minute. Let me ask this first. Let's say that I know that on average I'm going to move 2 1/4 turns. I want to know after 10 turns how many spots have I moved. So after 10 turns, how many spaces do I expect to move? So if I'm moving 2.25 spaces, or 2 1/4 times every time, after 10 turns, how many spaces do I expect to go? How could we find that out? So, you know, after 1, I expect to go 2 1/4. So after 2, I would expect to go 4 1/2. Yeah, exactly. Good, Bo. I'm just going to take this and multiply it by 10. I say I'm going to do that every turn. That's my, on average, I'm going to move that. Perfect. Just multiply that by 10. So I take that 22.5 and multiply it by 10, and I would expect to go about 2.25 and multiply it by 10, and I expect to go 22.5 turns. So after 10 turns, you're right, I would expect to go 22.5. So now here's Mr. Simpson's question. If I know that the board has 100 places on it, 100 turns on it, and I'm trying to figure out how long is this game going to take, how many turns am I going to have to suffer through. So if it has 100 spaces on it, how would I find out how many turns that would take? If 100 spaces, I don't have enough board. I'm going to erase this and write the question. If 100 spaces on the board, how many turns would I expect? So this time, this tells me, that way I was doing it if I know, well, it's going to take me 10 turns, I do it that way. Good. So now I'm going to do the inverse of this. Instead of multiplying, I'm going to divide. Great. So just take that 100 and divide it by 2.25. Tell me what that's equal to. How many is that? So if I do a couple of zeros on the end, it gets rid of the zeros. Gets rid of the decimals. And then I divide by 5 so that I get 2, 0, 0, 0. Divide this by 5 and I get 4, 5. I can divide by 5 again. I'm doing it the long way, I'm sure. 0, 0, divided by 9. 9 goes in there like 40. It's not going to be pretty. 4 is 36 with 4 left over. 4 with 4 left over. So I got 44.4 repeating, so it's going to take me about 44 times. Oh, good. Mine matched y'all's. Good, Jasmine. So about 44 times, 45 times, that's how long I expect for this to take. That's how many turns I expect. So you can see how we can figure out, once we know the average number of moves, then we can say, okay, in 10 turns, how far would I expect to go? And if the game has 100 moves, do I really want to spend this kind of time on it? Yes, that's a long game. So as a board game maker, maybe I want to start thinking about the average that I want. Maybe parents only want to spend 10 turns on the game. So maybe I only want to make the board have 20 pieces, 22 spots on it, 23 spots on it, so that it just takes 10 turns. But if I want a long game that's going to take us all night, then maybe I make a board game with 100 spots on it. So once I make that spinner, it can help me, and I know the average number of turns, I can decide how long to make my board game based upon that. Maybe you can use some of that information for this weekend's task. Tomorrow we're going to get to make our own board game and decide how long do we want to make it. Okay, so there's an example of finding that expected value. Let's do another one. Here's another. Suppose that you and a friend are playing cards and you decide to make a friendly wager. The bet is you draw 2 cards without replacement from a standard deck of cards. If both cards are hearts, your friend will pay you $75. Otherwise, you have to pay your friend $10. What's the expected value of your bet? So, first thing you're going to do is make a probability distribution. By the way, see the haiku for the day? Home to all to come, home to all already past. Wait, home to all to come, yeah. Home to all already past? That's not enough. Home to all already past. There we go. Home to all still here. Okay, cool. Home to memories past. Home to memories yet to come. How will you shape it? Sometimes these poems are like above me. I don't quite get it. Y'all tell me the meaning of that poem. Sometimes they're a little deep for me. Oh, yes. Bo, we could use hypergeometric when we see that without replacement. We start thinking that. But maybe this is even simpler than that because we're just going to draw two cards. So we're not going to do it repeated number of times. We're just going to draw two cards. But that's good. That's what you think when you see that without replacement. You start thinking hypergeometric as opposed to binomial. All right, let's now make our probability distribution and what are the potential outcomes? What could happen here? What are my outcomes? What do you think? Need another cup. What could happen? What could happen? Did I lose all y'all? Are you still there? If I'm playing the game, what could happen? There are, back up though, you're thinking way too deep. Just what could happen if I'm playing this game? For me, oh yeah, I like it. I could win or lose. There you go, nice and simple. Those are the outcomes. I could win the game or I could lose the game. Those are really the two things that could happen. Now, if I win, how much do I win? So, in this case, think about, we want to quantify those. We want to give these numbers. That win and that lose, in order to be able to find the average, the mean average, we have to have numbers with it. We have to have some sort of quantity with it. So, if I'm winning, how much am I winning? If I'm winning, how much am I winning? I'm going to move those up just a little bit. If I'm winning, how much am I winning? I'm winning $10, right? No, I'm winning $75. Yeah, thanks, Jasmine. $75. And if I lose, how much do I lose? I lose $10. Now, in order to show that I'm losing that $10, just like before when we went backwards 10, we set a negative number. Here, when I lose $10, to show that I'm losing, to put a quantity to that, I'm going to say it's a negative $10. So first I have to figure out what are my outcomes. Well, in this case, it's win or lose. And then in order to be able to find the average, we've got to quantify it. We've got to have some sort of quantity that goes along with that. Some sort of number that goes along with it. So in this case, if I win $75. If I lose $10. And those are my two outcomes. Now, I need the probability of each of those outcomes. So first task, what are the outcomes? And give those numbers. Second task, we've got to find out the probability. So how do I find out the probability? Now I can start looking at the probability. What is the probability that I win? How do I go about finding out that probability that I win? Well, to win, I need, if I win, I have to do 2 hearts. I have to get 2 hearts. So I have to get a heart and a heart. So in order to win, I've got to get a heart and a heart. And the probability that I get a heart on the first one Well, there are 13 hearts out of 52 cards. And, so there's that multiplication. The probability that I get a heart on the second one, well, I've taken stuff out of the deck. There's not a heart. I've already got one heart in my hand if I'm winning. So that means that there's only 12 hearts left out of 51 cards. Mr. Simpson, I think I lost them all. They're not helping me out here. Or maybe I'm going too fast. I don't know. Maybe the lag time's just really long. Okay, I'm going to simplify since I'm just multiplying here. So 13 over 52 is 1 over 4. These guys can be divided by 3. They add up, so I know that they can be divided by 3. So I've got 4 over, well, 3 goes in there 7 times. And then these 4s can cancel out. So that I end up with 1 out of 17 times. Did I do that right? Maybe it is just a lag. Y'all check me though. Did I do that right? Is it 1 out of 17? Then, if the probability that I get, okay, good. If the probability that I get a head and a head is 1 out of 17, then what's the probability that I lose? You're going to see. Oh, yeah, it will be good for... All mine are going to make a game also this weekend. So this is really perfect. There you go. Perfect, Priscilla. So I'm doing not heads and not heads for the next one. Now, oh yeah, Eve, it should just be the complement of this, right? It should end up being 16 over 17 so that it adds up to be 1. Because every time it should add up to be 1. But you're right, we could just do the math here and say, well, that's 39 not hearts out of 52. And once I've taken 1 out, then I've got 38 out of... Actually, that's not quite right. Because this is one way to do it. But couldn't we also do this? Or a heart and a not heart? Or a not heart and a heart? Oh, so I actually like Eve's method better because all of a sudden, doing it this way, we're going to have to come up with lots of different methods for coming up with not hearts. Because you're right, we could get a not heart and a not heart, but maybe I just draw 1 heart. And that heart could be here or there. So maybe probability is tricky. Maybe it's better just to use the complement there. So once I have one of the outcomes, then it's easier to find the other one. So that is super tricky. Now I would have figured that out in the end because watch. If I just do this one, we end up with 3/4 times, let's see, 38, 51, man, that's not nasty, that one doesn't come out, but then this goes in there, 2 goes in, 1, 9, and 3 goes in, we saw that a minute ago, 17. Notice that we weren't going to come up with the complement. So if we had gone through here and done it, that's why when you get your probability distribution, you're going to want to check to make sure that it adds up to be 1. Notice that 1 out of 17 plus 19 over 34 does not add up to be 1. So check each time, and if it doesn't add up to be 1, it tells you that you're missing something. Just like here, we could have gotten 1 heart and not a heart. So that's a good way to check yourself. Okay, now that that's the hardest part. Finding the probability distribution is the hardest part. Once we've done that part, then what we do is we take our outcome and multiply it times our probability. But step one is you've got to find that probability distribution. That's the hardest part here. So now I'm going to take my outcome and multiply it times my probability. So I've got 75 times 1 over 17. I'm going to go ahead and put a minus instead of a plus. 10 times 16 out of 17. So again, once I have that, then this is easy. I just multiply times its weight. If we did this 17 times, if I did the game 17 times where I drew 2 cards, I would expect one of those times for me to win. Now, in this particular thing, it doesn't really make sense to find an average. I'm just going to do it once. I'm either going to win or lose. But let's say that we play this game every day for a year or something. And I want to know, on average, how much am I going to win? Well, now all of a sudden I can find that average by doing this. So that's where the expected value comes in, is on average. If I repeated this over and over again, on average, how much would I expect to win? Or if I made this bet and then, Bo and Eve made this bet and whatever, so that we're doing it over and over again. You've got to repeat the experiment in order to be able to find the average, or to need that average at least. So here I've got 75 over 17 minus 160 over 17, which, what does that make? Have you already come up with it? That's right, Bo. If we'd have done all the different possibilities, we would have come up with 16 17ths. You're right. So on average, I'm going to lose, if I went down 100, I'd be at 60, but I need to add back 25. I think I'm going to lose 85 over 17. Did I do that math right? Remember, this is subtraction. So 160 minus 75, is it 85? Okay, good. Now we divide, and does that go in there 5 times? Let's see, 5 times is 50, 35, sure enough. Wow, it's so nice when the numbers come out pretty. So on average, I'm going to lose $5. So it doesn't sound like a bet I want to make, over and over again. It doesn't even really sound like a bet I want to do once, because I only win 1 out of 17 times. And then if I do it over and over again, I'm losing money. So, maybe I bet that on the other way. So if we did it 10 times, or if we did it 100 times, if I've got 100 people making this bet, or 100 times I do it, or over the year, let's say in a year, we play the game. Every day for a year, what do I expect to win/lose? So if I play that game every day for a year, what do I expect to win or lose? What do I expect the outcome of my bet to be? So I just take that -5 that I'm losing over the year on average times the 365 days. We'll assume it's not a leap year. And then we multiply that together. So 5 times 5 is 25, 32, carry a 3, 15, 16, 17, 18. So I would expect then to lose 1,825. Perfect. Man, I do not want to play that game every day for a year, unless I'm the one paying out $75 when they draw hearts. I only want to play it the other way around. Okay, so again, the way this works is you make your probability distribution first. Come up with your outcomes and give them a quantity. And then we put our probability with it, and then it makes it a lot easier to find the expected value. Okay, let's do the next one. One more here, and then I'm going to go back to our original and add a little something to it. Okay, so let's read this last one. A department store gives out coupons for $10 of free merchandise. Based on past data, 1/4 of the customers use the coupon but do not buy any merchandise. Okay, so I give out $10 coupons to everybody. And the people that come in, they 1/4 of them are just going to use the coupon, get $10 in merchandise, and be out of there and not pay me anything. Then 2/5 check out with $40 of merchandise, and then they use the coupon. So how much do they end up paying me? Think about that for a second. And then 1/5 use the coupon on merchandise that rings up to be $75. The rest do not take advantage of the promotion. So the rest of the people just are like, peace out, I came in, I couldn't find anything I like. All right, so what are my potential outcomes, or what as the company, I ran out of room for the question, so let me ask you the question. What is the expected value, or the expected, what's the expected value of the promotion? In other words, what's the expected intake from the company? How much are they going to make off this promotion of giving a... yes, that's right, Bo. This is why I never gamble. You're exactly right on that. You learn real fast that the house is going to win. The casino is going to win. That's all there is to it. Or you find some poor, unsuspecting fool to bet with where you already know the outcome is in your favor. One or the other. Okay, so what is the expected value of the promotion? In other words, what are the outcomes that could happen? So that's our first job every time, is to figure out what are our outcomes. So for this store, I don't know if y'all can read that or not, but for this store, the things that could happen are they could just use the coupon. So I'm going to write this down. They could just, not with that marker, I'm not going to. They could just use coupon. Or they could buy $40 and use coupon. Or they could buy $75 and use coupon. Or they could do nothing. I ran out of room. Okay, so now we want to quantify those. Every time we need to make it into quantities. That's right, Jasmine, we're going to make money or not make money. But even with the making of the money, we've got lots of different options on how much money we're making. And in fact, in this one, if they're just using the coupon, what's happening for us as the company, what's actually happening if they just use that coupon? If they come in, pick out $10 worth of merchandise, use their coupon and leave, what's actually happening for me as the company? Am I walking away with money, or am I losing money on that bet? Yeah, I'm actually losing $10, right? Because that's how much the coupon was. So in that case, not only did I not make profit, but I lost money. I lost $10 out of it. Because they walked out with $10 worth of my merchandise and didn't have to pay for it. And here, they're buying $40, but then they use the coupon, so really how much am I making? As the company, how much am I really going to make off of that? I'm not going to get the full $40 because I lost $10 with that coupon. So really I'm only making $30. And when they buy $75 and then use the coupon, again, really good. How much am I really making if they buy $75 and then the coupon? Yeah, it's $65. And then if they don't do either, if they're not using the coupon at all and they're not buying any merchandise, then what's happening? Well, then those last people don't do anything. I'm not getting any money off of them, but I'm not losing any money off of them either. So the quantities are not the P of X, my variables there are I lose 10, I gain 30, I gain 65, or just nothing happens at all. So as the store, these are my outcomes. So we came up with words, but then not only do we have to come up with the words, but we need to quantify those words too, the possible outcomes. Then I'm going to look at the probability of each. So what is the probability that I lose $10? So in this one, I think it just tells me that probability. I don't have to go through those probability rules that I've done in the past or use binomial or use hypergeometric or anything like that. I can just look at it and it tells me what the probability is. So tonight, you're going to be doing some where you're finding out that probability, and in some of them it's just going to tell you. So here it's 1/4, you're exactly right, of the customers that use the 10. And then my 30, well, it tells me again that 2/5 did that. So the probability that I just randomly grab a customer and this is what they're doing is 2/5 of the time. And then the 65 was 1/5. Uh-oh. How do I find out how many people weren't doing it? How do I find out that probability? How could I find out this probability right here? Perfect. Oh yeah, the complement. That's exactly right. This is going to be the complement of those. So I'm going to take these, add them up, and subtract from 1 to find out how many didn't do anything. And you're exactly right. We have to find a common denominator for that. So what would the common denominator be for 4 and 5? What would that common denominator be? What, 20? 4 times 5 is 20? So write this as 20ths. Oh, geniuses. Pure geniuses. Geniuses. All right, so this is 20ths. We'll have to multiply the bottom to get to 20, then I multiply the top to get to 20. Multiply the bottom by 4, multiply the top by 4. Multiply the bottom by 4, multiply the top by 4. I'm going to add these up and subtract from 1 to find out what the probability is that of 0. So I'm going to add all these up, subtract from 1, and that's going to give me the probability of 0. So the probability that I get 0 is 1 minus, well that's 13, 14, 15, 16, 17. I got 17 20ths. Is that what y'all got? There's definitely some lag going on today. It could be on my end. Maybe I'm not putting it out fast enough. My brain's definitely lagging. So 1 minus 17 20ths, well that's 20 20ths. over 17/20, which gives me 3/20. So the probability that they didn't do anything was 3 out of every 20 customers. There we go. 3 out of every 20. So these guys should add up to be full 1. So Priscilla, it all adds up to be 1. And so we were trying to find out the probability of that 0. And in trying to find out the probability of that 0, we needed to find the complement. So that's where that 1 came in. Because all of these add up to be 1. Okay, now that we have that, now that we have our probability distribution, so first thing we did was we came up with the outcomes, we quantified them, gave them a number, and then found a probability of each. Now, we're going to go through and do the multiplication. Now we can find the average. So the way we do the average is we just multiply our -10. So the expected value, remember we use that mean to be the expected value. Yeah, 20 over 20, that's also 1, right? I like it, yeah. But the 1 looked weird, yeah. Still 20 over 20. Okay, so I'm just going to take my quantity and multiply it times my probability. So -10 times 1/4 plus 30 times 2/5 plus 65 times 1/5 plus 0 times 3/20. So on average, will I get a negative? Maybe we should have just made all of these a common denominator instead. Because in the end, we're going to have to add them up. It might have been better to just write them with those 20ths to begin with, but we'll leave it here for now. 10/4 plus 60/5 plus 65/5. That on the end is just 0, so I'm not sure why we were worried about it, but there we go. That's how you find that probability in case you need it. Then we add across. So you got, well, let's do it this way. Oh, wait, I have to have a common denominator. I can't just add those. They need a common denominator. I was about to just add them. But we have to have a common denominator first. So again, I'm going to need 20 as my common denominator. I mean, I guess I could add these. They have the same they have a common denominator. So maybe we do that first? I don't know. What do you want to do? You do it one way, I'll do it another way. How about I add these first? I get 125 over 5. I'll go ahead and make this one into 50/20 times 5 to make that -50/20. And here I just added those together. I still need to make that into 20ths though. So -50/20. Multiply this times 4 over 4. So 20ths. 400s plus another 100 of 25s makes 500. I'm getting 450 over 20 in my little bitty spot down there. Yeah, that's looking good. Now I'm going to simplify so that here I divide by 10, I got 45 over 2. So divide 45 by 2 and you get 22.5. So on average, they expect to make $22.50 off of each customer. That's the average. So they're losing some money. Some people are coming in, looking, and leaving. But on average, they expect to make $22.50. So if they had 100 customers, come in, how much would they expect to make throughout that promotion? Well, then you just take that $22.50 and multiply it by 100. So they end up making $2,250. So, you know, if 100 customers, how much expect to make? Well, in that case, you do just 100 times that 2250. Good, y'all have got it. 100 times 2250, which is $2,050. Perfect. Okay, so big deal. First make your outcomes, then quantify it, and then your probability of each. I'm going to go back and do one last thing. By the way, y'all did a great job. We're having a few times that trolls are coming in, and I want you to know that y'all are handling them perfectly. Because this is just a public live stream, anybody can join the live stream. And so we may have throughout the time people who come in that do things like that are like, hey, can we start over? I'm late or whatever. Y'all are doing a great job of just ignoring them. That's the perfect way to handle trolls. If they don't get a reaction, then they'll just leave. They'll get bored. Either that or they'll stick around and learn some math. That'd be great too. I'd love for them to stick around and learn some math. Okay, I want to go back to this game right here. And let's pretend that this is a game at the fair that I've put on. I don't think so. I mean, could be. There might be somebody out there. If they are in my class, they should probably tell me who they are so they can get their bonus points. And I bet they're not reality. That's like my bet. Okay, I'm going to do something to this game just real quick. For our last problem here. I'm going to do one thing to our game. And that is, I'm going to make this a game at the fair. And if a player gets 0 heads, they win $5. If they get 1 head, they win $3. If 2 heads, then they win $2, and 3 heads, they win $1. Okay, and then it costs $2 to play. Okay, so we have this game at the fair, and you go up to the fair, and you get to win. No matter what happens, you are going to win some money. So you give the lady behind the counter $2, and now you flip your coin 3 times. And if you don't flip a single head, then they're going to give you $5. And if you flip 1 head, they're going to give you $3. And if you flip 2 heads, they're going to give you $2. And if you flip 3 heads, they're going to give you $1. Okay? So the first thing we have to do is figure out the outcomes. So this is a little bit tricky. We've already figured out the outcomes. We know that we could flip 0 heads, 1 head, 2 heads, or 3 heads. But let's quantify that so that we can find what is the expected winning for the game. How much do you expect to win for the game? Well, if I get 0 heads, how much do I expect to win? Yeah, now they're dollar amounts. So now my variables, while these are variables, these are outcomes, what I'm now looking at the winnings. So when I quantify it or give it a number, that's going to be the winnings, the associated number of the dollar value with it. So how much do I expect to win when I do $0? Now, Bo is totally fallen for my trap as the person who's running the booth. I want you to believe you're going to win $5. But are you really winning $5? Is that really what's happening? Because remember, it costs you $2 to play. So how much are you really winning? How much is that really happening? What's really happening? It seems like you're winning $5. Yeah, you're not really winning $5. It seems that way. Your kid walks away happy with a $5 bill, but you know that really you paid $2 to play, so you are only winning $3. Oh yeah, and then what about if I get one hen? How much am I winning here? How much am I winning there? One head is $3, so I paid $2 to play, so really I'm only winning $1. And then here, two heads, $2, so I come out even on that one. Cost me $2, I won $2, I just walk away with the same. And on the last one, 3 is minus $1. Whoever set this game up though didn't know statistics. The game person is going to end up losing money. Let's see though. So now, when I do this multiplication, 3 times 1/8, notice it changes that expected outcome because now it's based upon the dollar amount. I'm looking at that winnings. Minus 1/8. So I end up with 3/8 plus 3/8 plus 0 minus 1/8. So I've got 6/8 minus 1 is 5/8. So on average, I'm going to have to pay out over and over again. You're going to actually win money on average at this game if you play it. So that might be a good game to play. If the carnival is the one, if they're playing that game, the person with the carnival is paying out all the time. They're going to lose money. Not a good game for them. They should have put this minus $1 on one of these heavier ones. Made this one minus 1, then maybe that one 1, and maybe we would have done it. By the way, if on average, if your average equals 0, then we call that a fair game. In other words, if this had come out to be 0, what that would mean is I'm paying out just as much as I'm getting in. And we call that a fair game. That's fair. You got just as much as us, then it turns out to be fair. Okay, so big parts of this. The expected value is just a weighted mean. That's all it is we're looking at on average. If we repeated this over and over again, on average, what would happen? Then you want to find out your outcomes first and quantify them. Give them some number, those outcomes, and then find the probability of each, and then you're just multiplying and adding. All right? All right, go tonight and read those questions carefully, because tomorrow you may have those questions in your mind as you're making your board game to kind of help you prepare to make your own board game. So as you do the homework tonight, think about creating your own board game, because the questions tonight kind of lead into that. And if Jasmine wants me to send her my questions for expected value, just let me know, because they might help you when you're building those board games to have that practice of finding the expected value with other board game type problems. So just let me know and I'll send it to you. All right, guys, y'all have a great afternoon. Tomorrow we're going to Look at the task that you've been asked to do for the week where you're building up that board game. And I'll see y'all tomorrow. I'll see you on Discord here in just a minute. That's where I'm going to see you. You're all going to join here, do your homework, get it out of the way, get a Dropbox, be done with it. So then all you have to do is make a board game and play it. That's the plan. All right, see y'all in a bit. Math made simple. It's Simpson Math. Simpson Math. Thanks for watching.